Hello everyone. Today I wanted to tell you a little bit about a couple of papers that I find very exciting in the area of unsupervised learning and clustering learning. And these are all papers that came out in the very recent present, so in the last 2 or 3 years. I started working on clustering learning basically in the middle of 2012. When I had an idea about clustering to learn features quite independently actually. When I went home, I found out that just other people had previously, just the year before, started working on a similar topic. So I wanted to show you some of their work and some of ours before delving into the code. So one of the most important paper that they came out from our group recently is this clustering learning for robotic vision that we worked on basically very recently, just a few weeks ago, was published on arXiv. Before I go into that, let me tell you a little bit more about the group from Andrew Wang and in particular Adam Coates, that has done some previous work in the area of clustering learning and in particular learning with k-means and all for unsupervised deep network. So I'm going to tell you a couple of things about a few papers of his that are quite interesting, a couple of papers that I found quite interesting, and then I recommend you read them in full details. So the first one was a paper from 2011. It's called an analysis of single layer network in unsupervised feature learning by Adam Coates together with Andrew Wang at Stanford. So what they did basically, they compared a couple of deep network training for a single layer to see the performance. So one of the interesting things that they found, I'll scroll down the article, was basically how good clustering learning was working. So there's a section on clustering learning here, k-means clustering, where they tell you exactly how they worked up things. Particular, the difference with our papers and ours is that they used some kind of hard assignment nonlinearity, a triangle kind of nonlinearity that you can read here in section 3. It's basically sets a lot of it computes the mean of output of the features, and then it sets practically half of them to 0, and then everything that is above averages he basically keeps. So it's sort of implements some kind of a competition. There's a k-means hard and k-means triangle that are both implemented this way. The one in triangle, so the second one that I told you about, is basically quite effective. They also do this similar processing to convolutional neural network. It's a little bit slightly different in the sense that they convolve with the filters that they found with this clustering technique or other techniques. They convolve and then they step for a little bit, and then they convolve again, step, and so forth. And they create a whole bunch of feature vectors, and then for each basically quarter of the image, they divide this image, which is usually 32 by 32. They basically combine all the 4 vectors and all the channels together into a single vector, and then they use a classifier to classify each one of these regions separately. So it's a little bit different from a standard deep network COMNET, but it's quite similar ideas, basically the convolution and the kind of a pooling sampling idea. They also use a technique called whitening, that it's also used in convolutional neural nets, in particular by means of contrast normalization by widening. The way they used it is quite expensive and requires you to process the entire data set to basically try to get on every channel of the input a standard deviation of 1 so that you kind of maximize the signal to noise ratio of the input. And it's quite an expensive operation, and it's not really something that you can do all the time. It's quite costly for deep network, and because it's it requires you the use of large matrix operations. So we didn't really use them. What Adam Coates found is that he compared the different encoding techniques, autoencoders and unsupervised learning. And this is what he got with the k-means, with and without widening, and with other techniques like sparse autoencoders and sparse restrictables and machines and so forth. What he found that was quite interesting was that when he used k-means with a single layer on a CIFAR 10 dataset, which is a quite hard dataset, he found out that basically he could beat the state of the art at the time, multi-layer network with just a single layer with a lot of features, meaning 1600 features or 4000 features. And he can beat all this algorithm or get close to it. So it was a big splash at the time because apparently one single layer could beat multiple layers. So I really recommend reading this article. It's quite an interesting article. Second article by Adam Coates that I quite like also is the emergence of object selective features in a supervised feature learning. This is a more recent paper, just last year. And what they did basically is they took a lot of images random from YouTube, and they tried to figure out if the network trained unsupervised with the 2 layers of clustering learning was able to learn these features, was able to learn something that was occurring often, for example, a human face. This is similar work to the one that Google did last year with the Quackle, but with a much larger setup and with a very complicated stochastic gradient descent update of weights with the unsupervised technique. And they more or less found very similar things. So I find it quite attractive because these didn't require a lot of processing. They use 57 million 32 by 32 pixel patches. So quite a lot of data. A lot of patches had nothing, but some of them had a face. Reference 11 is the paper from Google that you can then look at by Quackle. So the algorithm is quite similar to the previous paper. So they use the k-means to find. They perform PCA widening before, and then they use k-means to learn a dictionary of samples. Then they basically pool similar units that they found. So k-means can return a lot of filters. They are very, let me get to the picture. K-means can return filters that are quite similar, but in different locations, in different, and they group them together into several groups, and then they basically max pool from each group for the first layer. Their network is this. It's basically, let me see if I can make it a little bit bigger. So the network that they use is basically has a 32 by 32 pixels that are grouped in group by 8 by 8. There's 64,000 features that are learned, and these 8 by 8 pixels are basically turned with the 9 by 9 filter, if I'm not mistaken. 8 by 8 pixel. yes, they're combining 4x4 64,000 features, from these groups you max pool the best. Then you do again k-means on all these groups, and then you max pool the best. And so these are the images that were given to the network. Just slightly bigger. The patches of 32 by 32 were learned here. So what they found is that basically this network was able to learn basically faces. The best the neurons in the network would learn, at the output of the network would learn some kind of was able to recognize and have a prototypical face. And the output from the first layer instead they just had the parts of a face, which means that the network was able to combine parts of this face together into a prototypical face. They also compared it to other kind of techniques, and they computed a precision recall of the output of this network, and they show that, for example, the first five, the best cells performed quite well, as opposed to simple cell that were trained on the full 32 by 32 patches. So the two-layer network was actually getting a big boost. And even a SVM trained from label data was not doing as well. It's a linear filter in here. So this is quite an interesting paper because it shows that you can learn without much supervision. You can find cells that respond to the most typical item or things in a data set. It's quite an interesting result.